Math is incomplete. That's probably the simplest description of Gödel's incompleteness theorem. But it's incomplete. It's not accurate. Let's make it more precise.
First of all, what does incomplete mean? In everyday language, incomplete simply means something is missing. But in mathematical logic, an incomplete system contains at least one statement that can neither be proved nor disproved. It means that mathematics cannot prove every statement to be true or false. Gödel constructed one such statement, the G sentence. This statement became the key to Gödel's proof of the incompleteness theorem. Now our sentence becomes, math contains statements that can neither be proved nor disproved. That's better, but proved where? Every proof takes place within a mathematical system. Different mathematical systems prove different things. Change the system and something that could not be proved may suddenly become provable. So we have within the system. But what exactly do we mean by math? All of mathematics? Geometry? Calculus? Number theory? Gödel's theorem does not apply to mathematics as one giant, undefined object. It applies to formal mathematical systems. A formal system consists of a set of axioms and precise rules for deriving new statements from those axioms. Euclidean geometry is a prime example of this. So we have a formal mathematical system. But is that true of every formal system? No, some systems are complete. So what kind of system does Gödel's theorem apply to? First, the system must be consistent. But what does consistent mean? A system is consistent if it never proves both a statement and its negation. For example, it must not prove both 2 plus 2 equals 4 and 2 plus 2 does not equal 4. If it could prove both, the system would contain a contradiction. And once a contradiction is allowed, the usual rules of logic can be used to prove anything, literally anything. So we have every consistent formal mathematical system. But does Gödel's theorem apply to every consistent formal system? Still no. Some systems are simply too weak. They cannot even express ordinary arithmetic. So how powerful must the system be? It must be capable of expressing arithmetic, not advanced calculus, not every area of mathematics. Just enough arithmetic to express natural numbers, addition, multiplication, and basic relationships between numbers. Why is that important? Arithmetic is already rich enough to represent mathematical statements and proofs using only numbers. Gödel discovered a way to encode mathematical statements and proofs as ordinary numbers. Once proofs become numbers, arithmetic can reason about them. And once a system can reason about its own proofs, it can express statements about its own provability. It can even construct an arithmetic statement that essentially says this statement cannot be proved within this system. That changes mathematics forever. So we have capable of expressing arithmetic. That sounds close. But one more condition is still missing. How are the axioms of the system chosen? There must be a finite procedure for deciding whether something is an axiom and whether a proof is valid. Otherwise, we could simply declare every true arithmetic statement to be an axiom. The system must be effectively axiomatized. So we finally have every consistent, effectively axiomatized formal system capable of expressing elementary arithmetic contains statements that can neither be proved nor disproved within the system. That is Gödel's first incompleteness theorem in a single sentence. Yes, it's a long sentence, but every word is there for a reason. Inside the system, those statements can neither be proved nor disproved. Outside the system, we can recognize that some of them are actually true. Every like, comment, and subscription helps this channel grow. Thanks for watching.